Start this lecture, chapter 8, still, sedimentation, one of the most important process in water treatment. Well, what is the meaning of sedimentation? It means that the majority of the particles will settle by gravity within a reasonable time and can be removed. Okay? These particles with density greater than 1,000 kilogram per meter cube will eventually settle because it's higher than the density of the water. And particles with density less than 1,000 kilogram per meter cube will float or will be suspended to the water, in the water surface. There are always common type of settling. There is a type of settling called discrete particle settling, and there is another type of settling called flocculent settling. Let's look at this discrete particle settling. Discrete particle settling occurs when the particles are discrete, okay, and they do not interfere with each other as they settle. Every particle are settling by itself. No interaction with other particles. For this type of settling, the movement of the particle in the water is determined by a balance of the downward gravitational force, an upward buoyancy force, and an upward drag force. So this type of settling and this movement of particles are governed by the settling velocity of the particle. And this will be governed by the law called Stokes law or Newtonian law. Now we will show you some tables in the next few slides, but before we do that, it is applicable here that we should assume that these particles are spherical, and when the Reynolds number is less than or equal to 1, it means laminar flow, because we are assuming that everything is free average. Everything is laminar, not turbulence flow. Newton's law is also used to determine that the settling velocity of particles when the Reynolds number is greater than 1 is something called transition and turbulent flow occurs. And that's some fluid mechanics. Let's look at the settling velocity S is equal to gravity constant G, diameter of the particle square over 18 viscosity. Of course, here is the acceleration due to gravity, and the second square, density of the particle, density of the kilogram per meter cube, density of the liquid, kilogram per meter cube, density, diameter of the particle, m, and m is the dynamic viscosity of the liquid, Newton second per meter square. For laminar flow, we should check it. CD is equal to 24 over Reynolds number. This equation is applicable for spherical particles, with a spherical shape. And when the Reynolds number is less than or equal to 1, which means we are applying this law for laminar flow. Of course, this has limited application in water treatment because conditions in most treatment facilities are not laminar. Let's look at the next one, Newton's law. Of course, settling velocity, square root of 4g, density of the particle minus density of the fluid, diameter of the particle over 3, CD, if you took water resources, you know what CD, times the density of the liquid. Okay. As we said, G is meter per second square, density of the particle, kilogram per meter cube, density of the fluid, kilogram per meter cube, and CD is the drag coefficient. Now we went from laminar and we came to transition flow. CD is according to this equation. This is from water resources, and this is a well-known equation. Of course, in turbulent flow, CD becomes constant for Reynolds number higher than 10,000. This is applicable for particles when Reynolds number is greater than 1, transition flow, and turbulent flow. Okay, let's look at this application. Calculate the terminal settling velocity for a sand particle. Now we're talking about sand particle that has a diameter of 100 micrometer, density of 2,650 kilogram per meter cube. The water temperature is 10 Celsius. Okay, we put the Stokes equation, and now we need to find out terminal settling velocity of the particle. And first of all, we have the temperature of the water is 10 Celsius. We could find out the density of the water, 999 kilogram per meter cube. This could be found from tables, and it will be given to you in the exam. The viscosity of the water is 1.307 10 to the minus 3 Newton second per meter square at this temperature. And of course, this is the dynamic and kinematic viscosity in the same time. Okay, so we know G, we know the density of the particle, we know the density of the water, we know the diameter of the particle. Of course, we have to put it as this is 100 micrometer, 100 times 10 to the minus 6 meter. So two zeros here and 10 to the minus 4. So 1 10 to the minus 4 meter, and this is square. This is diameter, it has to be square, over 18, viscosity 1.307. You don't put this one, you put this one, mu. And now, of course, if you cancel out all the units, you will end up with what? Of course, here you will end up with second. So let's convert the second to hours. So 1 hour is equal to 3,600 per second. Of course, 1 hour to a minute, and minute to seconds, 60 times 60. And this would give you 24.8 meter per hour. Which means, if you have a tank, this tank is filled with water, this sand particle will move 24.8 meter for each hour of settling time. Now, before we proceed, we have to check if the Reynolds number is less than 1 or higher than 1. So the Reynolds number from water resources or from the previous classes you took is diameter of the particle times the settling velocity over v. Remember, there is mu and there is v. That's at the same temperature. Of course, you find this at the same time. Remember here in the Stokes law, we were using the dynamic viscosity for the Stokes equation. But the other one, we are using the kinematic viscosity. So this is kinematic and this is dynamic. We put the diameter, we put the velocity, and of course, since the kinematic viscosity is per second, you have to convert this hour to seconds, and you'll end up with 0.53. Oh, nice, less than 1. So, since the laminar flow exists, Stokes law is applicable. So the settling velocity is 24.8. We don't have to modify it. Let's look at, sometimes you cannot apply Stokes law. We have to apply Newton's law. Calculate the terminal settling velocity for a sand particle. The diameter is 200 micrometer. Density is 2,650 kilogram per meter cube, and the water is 15 Celsius. Of course, at 15 Celsius, density is 999.1 kilogram per meter cube. Mu is 1.139 10 to the minus 3. And V is 1.139 10 to the minus 6. Kinematic and dynamics. We put the Stokes law, and we plug in the numbers. You will find out 113.8. Wow, very fast one. Let's check on a number. You apply with, of course, here you use dynamic, and here you use kinematic and dynamics. So real number here, we use V here, so you'll end up with 5.55. That's greater than 1. So real number is showing that this is not laminar. So you cannot apply Stokes law. Stokes law is not valid in this range. So now we have to apply the other method. We should remember CD, the equation CD? 24 over RE plus 3 over square root of RE. So the RE was 5.55. 24 of RE, 3 over square root of RE, plus 0.34, remember, plus 0.34. I did not, these numbers are constant. Now we found out CD is 5.94. Now we do Newton's settling velocity. We apply the same equation we have in this table for G, density of the particle minus density of the fluid, diameter of the particle over 3 CD over rho. Okay, so we have everything, and you'll change second to hours. You'll end up with 97.1 meter per hour. Now we should calculate the number again and check. And then check the drag coefficient again and the terminal settling velocity again. We have to do several iteration, and when the value is convergent, is coming up to a good answer, now the settling velocity begins to converge. You can see it here. First of all, we get first trial 5.5, CD is 5.94. You find the answer of settling velocity is 97.1. And now we do Reynolds number here. Reynolds number would give you 4.74. So you find CD, and then you find from the equation 90.9. Now we are using the Newton's equation. We're not using Stokes law. We do find the number here is 4.43. It will give you CD of 7.18, and then you could find out the new settling velocity. Now you can see that the settling velocity will go down, 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 until here you can see that there is a convergence. So the settling velocity of this sand particle is 86.5 meter per hour. The number was almost 4.22, which is high, still higher than laminar flow, and CD is 7.49. So this is the settling velocity that should be the solution of this problem. During sedimentation, the particle settling follows some trajectories. And let's assume that this is the tank, a rectangular tank we have here, and that particles, they move horizontally at the same velocity as the water. You can see it. The particles are moving horizontally as the same velocity as the water, and are removed by gravity once they reach the bottom of the once they reach the bottom of the basin. So this is the bottom of the basin. And of course, the water is moving that way because the water is coming out from the other side. So this is the fluid velocity, and this is settling velocity of particle 1 and the settling velocity of particle 2 and 3. This settling velocity for discrete particles is constant because the particle will not interfere with the sound. At the top of the basin sedimentation time. Detention time. Sometimes they call it HDT, hydraulic treatment time. So, the critical particle settling velocity, sometimes they call it overflow rate, and that's good for the design. Once we come and design tanks and design reactors, we need to check OR. OR is the overflow rate. It's equal to the ratio of course, the critical velocity is h naught over theta. And theta, remember the time, is equal volume over Q. Remember volume and Q so it's time volume over Q. And also volume. What is volume? What's volume of the tank? Remember, the volume of this tank, it's area times h naught. So area times h naught, and h naught and Q, h naught would cancel with h naught. So VC is equal to what? Q over A. So V critical is equal Q over A. And the other name of V critical is OR, overflow rate. Of course, area is the surface area of the top settling basin in meters square. And Q, we know the Q is flow rate, meter cubed per hour. It is important to understand what is OR now. It is the overflow rate. Look at this. OR is not a function of the tank depth. Is not a function of the depth, because the depth was cancelled out. OR is not function of the depth. This is very important, and that might come in the multiple choice. You should understand this. The OR is also written as meter cubic per meter square per hour as a unit, and sometimes they call it, if you cancel out meter square with meter cube with meter per hour, sometimes they call it meter per hour, but most of the time you'll see it like this unit. And OR, overflow rate, is also called the critical settling velocity, VC. Now, let's look at the guidelines. Any particle with a settling velocity greater than V critical or greater than OR, then this will be removed. The particle will be removed. Particle with a settling velocity less than VC, now, this can be removed depending on the position at the inlet. Where is the location of that particle in the inlet? It could, it's possible, but the other one will be removed. If the particle settling velocity Vs is greater than Vc, it will be removed. So let's go to the figure 8.12, the one we just showed here. This particle number 3. You can see that Vs3 is faster than Vc. It will be completely removed. So for the particle in that example, it has a settling velocity greater than Vc, critical, so it can be removed because of its inlet position, very close to the bottom. Also in the same figure, particle 1 will not be removed. Why? Because the settling velocity is less than Vc relative to its entry point into the sedimentation basin. So the percentage, sometimes if you have a lot of particles in the reactor, and you want to find out the percentage of particles removed, if you divide Vs, settling velocity of that particle, over OR times 100, you can find out what is the percentage of particles removed. Let's look at this example. A treatment plant has a horizontal flow sedimentation basin with a depth of 4 meters. So you have a horizontal flow sedimentation basin with a depth of 4 meters. So there's a tank. Okay, so the depth is 4 meters. The width is 6 meters. The length is 36 meters. Oh, that's not according to scale, but. And the process flow is 450. The flow, the charge, 450 meter cubic per hour. So the flow is going that way. Of course, it's flowing from the other side, from here. What removal percentages should be expected for particles that have a settling velocity of 1? Percentage of removal of any particle with a settling velocity of 1 meter per hour, any particle with a settling velocity of 2.5 meter per hour. What is the minimum size of particle that would be completely removed? The size, diameter. Assume that the particle density is 2650 and the temperature is 10 Celsius. Okay. Let's look at this. Overflow rate or velocity, critical velocity. It has nothing to do with the depth. So it is the charge over the area. The charge is 450 and the area is what? The area, if you go back to the, let's go back to the other one. The area is what? It's 6 times 36. That is the area. 6 times 30. Don't multiply it with the depth. Only the area. Okay, the width and the length. This would give you an overflow rate of 2.1 meter cubic per meter square per hour. Now, we can compare this with VS, the particle and the second particle. The particles with settling velocity of 1 meter per hour, such as this, 2.1. VS here of this particle is smaller than 2.1. Okay? Less than the V critical, which means that the percentage of the removal is calculated using the equation. Fraction of the particles removed in percentage VS over OR. So you say that particle is 1 meter per hour over OR, so 140. Which means that 48% of these particles will be removed. The rest is going through the other. Let's look at the second particles with a velocity of 2.5 meter per hour. Again, 2.5 meter per hour, and the OR is 2.1. Oh, this is greater than the overflow rate. Okay? All particles with this settling velocity will be completely removed. They are fast. You can see they are faster than also the overflow rate. So you could do it like this: 2.5 over 2.1 times 100. It will give you over 100%. What is the meaning of this? A fraction of this particle is 1. Okay, 100% of these particles will be removed. And here 48%. The rest will be going to the next tank. What else he need? He need also to find out what is the minimum particle size that will result in a complete removal. To have a complete removal, Vs has to be equal 2.1, which is the overflow rate. We should plug it into Stokes law and check the diameter. Now, of course, he told you that the water temperature is 10, so we find density, mu, and v. So we have the gravity, density of the particle, density of the fluid, diameter is unknown, 18, viscosity, of course, hour to seconds, second to hours. And we have it as 2.1 because Vs should be equal to Vc if you want to make sure the 100% removal to find out the diameter size. From this, of course, here the diameter is square. So diameter, if you rearrange this equation, it will give you 4.48 10 to the minus 10 meters square because everything is in meter. Diameter of the particle is 2.9 10 to the minus 5 meter, which is 2.9 10 to the minus 3 centimeter. Now we have to check Reynolds number and to see if it's below than 1. So Reynolds number is equal to diameter of the particle settling velocity over v. So diameter, settling velocity, of course you have to make sure the units are consistent because here it's in seconds. V, this would give you a number 3.8 10 to the minus 7. Oh, that's nice. Less than 1. It's laminar. So the diameter of the particle should be 2.9 10 to the minus 3. Oh. So, because laminar flow exists and Stokes' law is valid. So, this is a horizontal flow tanks. So, this tank, as we mentioned, the flow of the water is horizontally occurring. So, the water is moving from this, water is moving the other side. So, we are looking about calculating the particle that will be settled at the bottom of this tank. So this is a horizontal settling tank. We could design it and we could operate it without the use of mechanical rakes and mixing. There's no mixing and there is no other moving part that require energy and maintenance. And of course, there's no money and there is no spare parts in this sedimentation tank. Okay? Typical detention times for rectangular sedimentation basin. Remember now what's detention time. The time it will take these water to be stayed inside the sedimentation tank. With a horizontal flow, of course, no vertical flow here, are 1.5 to 4 hours. This is the design detention time. There's other important criteria in our design we have to take into consideration. Number of basins, more than 2 or so on, can be taken offline for maintenance. Also, the basin depth, 3 to 5 meters. The horizontal mean flow velocity, 0.3 to 1.1 meter per minute. And overflow rate, 1.25 to 2.5 meter per hour. Length to depth ratio, 15. Length to width ratio, 4 to 5. And this is all going to be used for our design consideration later on once we design a horizontal flow sedimentation tank. Of course, there's other material that can be set by placing the basins side by side so they are share common walls, and of course integrating the flocculation process into the front sedimentation basin. Of course, if you want to combine flocculation and sedimentation, this typically requires diffusers. Of course, diffuser walls to separate the two processes. The wall has small hole opening of diameter of 100 to 200 millimeter, and the inlet structure to the sedimentation basin is also designed to provide uniform distribution of the water over the entire cross-section of the basin. And of course, maintain an appropriate velocity that not only prevents sedimentation at the inlet zone, but also limit the breakup of the formed flux. Flux particles they are coagulated together. A velocity of 1.15 to 0.6 meter per second will maintain the flux suspension for most drinking water application. And of course, sometimes you will have circular sedimentation tank. Can be designed and particle size removal is evaluated using equations that we listed before. We did talk about these types of settling. We talk about type 1. These are particle settling discretely. Remember discrete settling? This is type 1 settling. And we could remove grit. For example, sand, inorganic. There's another type of settling called type 2. Particles flocculate here during settling due to velocity gradient of fluids or differences in the settling velocity of the particles. Their sizes are increasing and they settle faster as time passes. Where this happens, of course, the particle size increases because of coagulation process and most conventional sedimentation basin. Type 3 is the third settling type. Blankets of particles, they just come into a junk. It comes into a pile of particles together, formed at high particle concentrations above 1000 milligram per liter. And of course, there is a clear interface is observed between the blanket and the clarified water above it. Of course, that happens when you have lime softening the sedimentation and in wastewater sedimentation and sludge thickeners. We will do filtration in the next